Welcome back. Let's consider a gusset plate that is subjected to the forces of four members, as shown in the image. This point here, this is where the lines of action of all the forces meet. Let's call this point O. And let's also consider it to be the origin of this XY frame. So you have one force, which is Fa equals 8 kilonewtons. Then you have another force, Fb. Then you have another force, Fc equals 12 kilonewtons. And then Fd equals 5 kilonewtons. Note that Fb is unknown. Furthermore, this angle is 45 degrees. Also, this angle is 45 degrees. And then you have this angle, which we call theta, and let it be unknown. And so what we need to do here, we need to find Fb, and then we also need to find theta. So as you can see, we have two unknowns here, and we have to find them. Now, if you look at this image, then you know that even though you have forces here, this gusset plate is not going anywhere. It means that there is no acceleration here. The Newton's second law says that for a constant mass, F net, or the sum of all the force vectors, equals mass of this object times the acceleration of this object. But since this object is not moving anywhere, this entire term becomes a zero vector because your acceleration is zero. In other words, I can write that the sum of all the forces in the x direction equals 0, and the sum of all the forces in the y direction also equals 0. Or alternatively, I can write the sum of all the forces in the x direction times I plus the sum of all the forces in the y direction times j equals a zero vector, meaning that it's 0 times I plus 0 times j. So this concept is called the equilibrium of a particle. And the main idea behind that is exactly this. All the force vectors that are applied to an object, if you sum them all up, then the net force vector must be a zero vector. What happens if this one here does not equal to 0? Then this object will start accelerating either in the positive or in the negative y direction. Or for example, if this one is not 0, then the plate will start accelerating in the positive or negative x direction. And if that happens in a structure, then it's very dangerous because the structure will simply collapse. This plate is part of some kind of building, so if it starts moving, then we are in trouble. And now, if we have to find forces or other unknowns, like this angle theta, then in order to do so, we first make a sketch of the object that we are analyzing, and then we list all the forces that are acting on that object. And this is exactly what we have done here. We have drawn the force vectors and the angles, and if we don't know a force or an angle, then we keep it as a variable, which is exactly what we have done here. We will find it later. We also clearly define where the positive x and positive y axis are relative to that object. And this kind of sketch with all these force vectors is called a free body diagram, or simply FBD. And in general, these kind of problems where you have to find forces or other unknowns, they are called equilibrium problems of a particle. We say particle because the lines of action of all the forces meet at this point O, and that means that instead of drawing this entire plate, we can equivalently take this point O, then put it right here, draw the same forces, the same coordinate frame, the same angles, and so this free body diagram is equivalent to this free body diagram. In the end, force FB and the angle theta will be exactly the same. Either we draw this object here, or we simply apply all these forces to this particle at O. It makes no difference. Meaning, the size of your object doesn't matter. The way forces act on this object, it makes the size of this object unimportant. And then you can just take the point where the lines of action of all the forces meet, and then treat that point as a particle and apply the forces to that particle only. And if you can do that, then you're dealing with equilibrium problems of a particle. And this is what this section will be about. Later on, we will learn about how to solve equilibrium problems for rigid bodies, but not in this section. In this section, we will stick with the equilibrium problems of a particle. And so when you solve for these kind of problems, then the first step that you have to make is construct a free body diagram, either like this or like this. And then once you have your free body diagram with all the forces and angles, and you have clearly defined where your positive x and y axes are, then you apply this particle equilibrium principle. And so you do that by writing out all the forces in the x direction and equating them to 0, and then in the y direction as well, and equating them to 0 as well. So I write the sum of the forces in the x direction equals 0. This arrow here shows that positive x is to the right. Then I put a colon, and then I write Fa plus Fb times cosine theta. That will give you the x component, and then plus Fd times cosine 45 degrees. Again, that will give you the x component of this Fd vector, and you make it equal to 0. And then you write the sum of the forces in the y direction equals 0. This arrow shows that positive y goes up, so colon, and then you have Fb times sine theta. That will give you the y component of this force vector, plus Fc, which only points in the y direction, minus Fd times sine 45 degrees. Now that will give you the y component of this force vector. But why do I have this minus here? I have this minus here because this Fd vector, it has a negative y component. It has a positive x component, but it has a negative y component. And that's why I have minus here. And then I equate it to 0. And so you know what your Fa is. It's 8 kilonewtons. You also know that your Fd is 5 kilonewtons. And then Fc, that's 12 kilonewtons. And again, this Fd, it's 5 kilonewtons. So in the end, you have this system of equations. You have two equations, and then you have two unknowns, Fb and theta. And now you can solve for these two variables that you don't know. We can take this first equation, and we can rewrite it like this. Fb times cosine theta equals, and then I put everything else onto the other side of the equation sign. And so I have this one here. And then I can put parentheses here, divided cosine theta, so it will go away from here. And now I will take the second equation and I replace this Fb with this expression here, because this is my Fb. So this is my FB, it's this one here, times sine theta, so I'm just going to put it here, and then plus 12 minus 5 times sine 45 degrees, it equals 0. You know that sine theta over cosine theta equals tangent theta, and so in the end I can rearrange this equation in such a way that I will have tangent theta equals, and then this ratio here. I have simply rearranged this equation here. And now in order to get theta, you simply need to take the inverse tangent and then this ratio, and then you get your theta. And if you do that, then you will have 36.27 degrees. So your theta equals this number here. And now you have your expression for FB, which is this one here. You know your theta, which you can put here. And so that means that you will have FB equals, and then this result here. So this one here, that's your theta. And so your FB equals minus 14.3 newtons. That's your FB. Then note that your FB is negative. What does it mean? Well, if you look at your free body diagram, then note that we assumed FB to be in this direction, towards point O. But we don't know if that's the case. Instead of this, FB could be like this. It could point away from O. And so if you don't know which way the arrow goes, then that's okay. You simply assume direction. You simply choose whether you draw this arrow like this or you draw it like this. That's your choice. Based on that choice, you will have slightly different equations. We chose FB to be like this, and that's why these were our equations. However, if we had chosen FB to be like this, so the arrow points away from O, well then you would have had a negative x component for that vector and a negative y component for that vector. And so then, in this equation, instead of a plus, you would have had a minus. And also here, you would have had a minus. But here's the thing. Once you choose the direction for FB, and then in the end, if your FB ends up being positive, then your assumption was correct. But if it turns out to be negative, then the force vector is opposite to what you had previously assumed. So if I initially assume that FB is like this, and if in the end my FB had been positive, then my FB really would have been like this. But if it ends up being negative, which is our case, then in reality, FB points in this direction. So from this minus sign, I see that this arrow actually points in this direction. However, if I initially, when I construct this free body diagram, when I initially assume that this vector is like this, then if in the end FB is positive, then my direction is correct. However, if FB is negative, then that means that in reality, this arrow points in this direction here, towards O. So when you find your force and it's positive, then that means that your initial assumption was correct. But if it's negative, that means that your initial assumption was wrong. In reality, the force vector points in the opposite direction. So that's how you do it. Thank you very much. Welcome back. So I have a traffic light here that is hanging thanks to these two cables. The mass of the traffic light is 12 kilograms. We define the coordinate frame to be like this. X is positive in this direction and y is positive in this direction. And so we can determine the slope of this cable like this, with this right triangle, and here the angle is 12 degrees. And so my question to you is, what's the force in cables AB and AC? What kind of tensile forces do they experience? Also, the gravitational acceleration is 9.81 meters per second squared. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this problem. This is a particle equilibrium problem, and we will start with drawing a free body diagram. And the particle in consideration here is this A, point A. So let it be here. First of all, due to the traffic light, you have a gravity force down, or weight, which is mg, or 12 times 9.81 newtons. Or we can simply write it 12g newtons. Then you have another force that goes along the cable. This is FAB, and here you have 12 degrees. And then here you have another force, FAC, and so here you have your right triangle, 24, 7, and 25. So this is our free body diagram. And now we will simply apply our equilibrium principle. We clearly define that positive x is in this direction and positive y is in this direction. So I write the sum of fx equals 0, and that gives me FAB times cosine 12 degrees minus FAC times 24 over 25 equals 0. With cosine 12 degrees, you obtain the x component of this FAB vector, and then with this ratio, 24 over 25, you also obtain the x component, but now of this force, FAC. Let's say if here you had an angle here, let's say psi, then this ratio here, it would be cosine psi. And now the sum of Fy equals 0, and so you have FAB times sine 12 degrees plus FAC times 7 over 25 minus, and now this force here, 12g, and it equals 0. So with sine 12 degrees, you obtain the vertical component of FAB, and then with this ratio, you obtain the vertical component of FAC. Again, if you had an angle here, psi, then this here, it would be sine psi. And so, you have two equations and two unknowns, FAB and FAC. So let's take the first equation. You can rewrite it like this. FAB cosine 12 equals FAC times 24 over 25. And then, in order to get rid of this cosine 12 degrees, you put it here in the denominator. So now you have FAB in terms of FAC. And now we take the second equation, and instead of FAB, I write this expression. So that's FAB, and then here I have sine 12 degrees, so I'm going to put it here as well. Then plus FAC times 7 over 25, that's this term here. And now I have minus 12g, and I can put that to the other side of the equation sign. Now I only have FAC here. Also, this thing here, it's tangent 12 degrees, and so I can factor out FAC, and all that equals 12g, and so here I will write FAC equals 12g over, and then all this, and that will give me 243 newtons. So that's your FAC. And now, in order to calculate FAB, you put 243 newtons here into this variable. And so FAB equals, and then all this, that's this expression here, and that will give you 239 newtons. And here is your answer. FAB equals that much, and FAC equals that much. And that's the sequence. You start with a free body diagram, you apply the equilibrium principle, you get your equations, and you solve for your unknowns. Thank you very much. Welcome back. So I have another traffic light exercise for you, but now you have two traffic lights. You have this one, its mass is 10 kilograms, and then you have this one, its mass is 15 kilograms. And so here you have 15 degrees, and here this theta angle is unknown. And now the question is, what is force FBA, FBC, FCD, and then this angle theta? So try it out by yourself. Try to find out what these four variables are, and then see the solution in the next video. Thank you very much. Welcome back. So let's now solve for these variables here, these three forces and the angle theta. Now we have four unknowns, but we can also construct two free body diagrams. Let's first take point B, and first of all, you know that you have a force of gravity here, which is 10 g newtons, because the mass here is 10 kilograms. Then you have this force, FBA, and then you have 15 degrees here, and then you have this force here, FBC. And now we can take another point, which is this C point, and here FG equals 15g, because your mass is 15 kilograms here. This is FCD, here you have your theta, and now if here you had a force from B towards C, note that we could have also written it like this, FC with respect to B. And here, for example, it could have been FA with respect to B, or FBA without this slash, meaning that the force goes from B towards A. But anyway, here you have a force that goes from B towards C. And here you have a force which goes from C towards B. But since you only have one cable here, then essentially you have this situation. So this is the cable that you have here. This is point B. This is point C. And so this is FBC. And due to the Newton's third law, this is the same force. And then here you have FCB. And again, here you have FCB. Since this cable is not accelerating anywhere, it means that minus FBC plus FCB equals 0, because we assume that this is positive x and this is positive y. And therefore, FCB equals FBC. So essentially what you have here is Newton's third law, action-reaction. And so now that we have two free body diagrams, let's apply our equilibrium principle. Let's first do it for point B. Again, the sum of all the forces in the x direction must equal 0, and the same thing in the y direction. So this is the equation in the x direction, this is in the y direction, and now let's do the same thing for point C. We apply the same principle. This is the equation in the x direction, and this is in the y direction. And so now you have 4 equations and 4 unknowns. You know that FBC equals FCB. The only difference between them is that they are in the opposite direction to each other. And so let's take this first equation and I'm gonna rearrange it like this. FBC equals FBA times cosine 15 degrees. Now if you look at the second equation, then you can find your FBA right away. You simply write FBA equals 10G over sine 15 degrees. And right away you know that FBA is 379 newtons. That means that in here you can say that FBA is 379 newtons times cosine 15 degrees, and that means that FBC equals 366 newtons. Then let's take the third equation, and here you can say that FCD equals FCB over cosine theta. Then let's take the fourth equation and let's rearrange it like this. FCD times sine theta equals 15G. Now if you remember then, FBA in the second equation, it was this one here. That means that FBC, which was FBA times cosine 15 degrees, essentially you can write it like this. 10G times cosine 15 degrees over sine 15 degrees. Now you know that sine theta over cosine theta equals tangent theta, but it also means that cosine theta over sine theta equals 1 over tangent theta, which means that here FBC equals 10G over tangent 15 degrees. But remember, FBC also equals FCB that you have here in the third equation. And so that means that here I can write this one, which is FCB, divided by cosine theta, so it's really 1 over cosine theta here. So that's your FCD. And now I will take this FCD and I put it here. I'm gonna make the substitution. And so you will have this one, which is FCD times sine theta, which I can put here. And now this one here, it equals tangent theta. So in the end, in the fourth equation, you have 10G times tangent theta over tangent 15 degrees equals 15G. And now we can cancel out the G's, and your tangent theta will be 15 times tangent 15 degrees over 10. Then you can find theta like this. You take the inverse tangent of this ratio and you will get 21.9 degrees. And now you can take your 21.9 degrees and you can put it inside here. You can replace this theta with 21.9 degrees. And so in the third equation, FCD equals 10G over tangent 15 degrees times 1 over cosine 21.9 degrees. And that gives you 395 newtons. And there you go. FBA equals 379 newtons. Then FBC equals 366 newtons. And also FCB equals 366 newtons. Then FCD equals 395 newtons. And then theta equals 21.9 degrees, which is this angle here. And as you can see, all the forces are positive, which means that the assumptions that we made for the directions of our force vectors were correct. Thank you very much.